Awesome. Thanks, Brian. Appreciate it. All right. So my name is Seth Schneider, and I am a product owner for Intel GPA. So how many of you guys are game developers? I mean, it's a game developer talk, probably a lot of you, right? Okay, great. How many of you are developing on an engine? Okay, the large majority of people, right? Okay. So what is Intel GPA? Intel GPA is a suite of tools that helps you optimize your games, right? So all of us are game developers. How do we use this thing, right? So let's just say you have your game and you've gone through the stages, you've implemented the basic functionality, you have your core loop there. You go, you run your game, you click the play button in your Unreal Engine and you go, oh man, my performance is not where I wanted it to be. All right, we've all had that experience. Optimization isn't one of those things to where it's an unfortunate happening in your game. It's part of the process of making your game, right? Everybody hits the performance optimization step. And that's where Intel GPA comes in, right? So it helps you go from that step of 30 FPS or whatever FPS that you're currently at when your initial functionality is done to hitting your FPS target. That changes per game titles, right? For mobile, maybe 30 is great. For a shooter, you pretty much want to be at 60 at all times, right? So depending on your target, you can use Intel GPA to help you get to that performance target. So before we kind of talk about the speeds and feeds of this awesome suite of tools, let's kind of understand how the architecture is built. So we use what's called a host target architecture. So the host system is a system that's running your analyzers, right? So this is where the analysis is taking place. This is where GPA is primarily running. And then the target system is the system that your game or application is running in, right? So you have your application running on your target system. You've connected it to your host system, and that way you're reading out live metrics and performance data of your game. That way you can analyze and optimize it without having a lot of overhead. So next, we can talk about the speeds and feeds. So this is like a giant eye chart for a lot of us. I don't want to go through all this stuff, but I can kind of hit some of the highlights. How many of you guys are developing a Windows game? Okay, that's a good majority of people. How about Android or mobile or iOS? Okay, so about a little bit less, but about half and half. So for Windows gaming, we support Windows 7, 8.1, and 10 on the host OS and on the target as well. For DirectX, we support 9 through 12. We actually do have some pretty good DirectX 12 support, is what I'll be showing you in the demo today. I don't want to go through a ton of slides, so we'll jump into the demo as soon as possible, but we'll be showing a DirectX 12 game today, highlighting some of our new DirectX 12 profiling features. So for target hardware, we support Intel GPUs, obviously. We also support NVIDIA and AMD GPUs. So let me talk about that for a second. So for Intel GPUs, we get all of our hardware metrics, and you can basically dive into your frame a lot deeper with those metrics. For NVIDIA and AMD, we get baseline API metrics, right? So we have access to our driver, so we can get all those metrics. But for AMD and NVIDIA, we don't have access to their drivers because we're Intel. So, but we do give you base API metrics and the ability to still look at your game and look at your game's performance, even if you're not using our hardware. So that's pretty cool. We can basically help you optimize on whatever hardware that you're looking at. For Android gaming, basically we support all the flavors of Android that you'd want, 4.x, 5.x, all the way through Marshmallow. That's using OpenGL 1.0, 2.0, and then 3.0 through whatever. So other platforms that we also are looking at are at Ubuntu gaming as well. So for like Steam Machine or whatnot, you can do that and actually analyze core GL apps. So it's kind of an eye chart. We can talk about support all day long, but let's get into some of the more interesting parts of GPA. So what's inside this suite of tools? First of all, we have Graphics Monitor. Graphics Monitor is the backbone of Intel GPA. This is the guy that sits in your task tray that basically collects all the data and is the interface between your host and your target. So if you want the same host and target, you can do that very easily with GPA. Graphics Monitor is the way to do that. So in the demo, we'll get to see it a little bit more in some of its awesome features. Some of the things that you can do in Graphics Monitor is like configure your experience. So for instance, one of the things that you can configure are triggers, right? So in a lot of profiling tools, you'll be playing your game and you're like, I know that there's this one FPS drop at, on the second level or whatnot, and it's hard to actually hit the button and capture that exact frame that is that drop. So you can set the triggers up in monitor to say, okay, if I reach below 20 frames per second, I want to take a capture or I want to dig deeper into my profile. So it's easy, right? So it automatically sits there and watches your performance for you and then triggers where the actual hotspot is. So next we have System Analyzer, which is the live analysis portion of the workflow, which we'll talk about in just a second. This is basically like Windows Performance Monitor, but on steroids, right? It has CPU performance, GPU performance, memory, pretty much anything that you'd want to be able to look at in real time. We have counters and collectors that sit there and basically show it to you in a meaningful way. There's some other cool features with System Analyzer, but we'll move on to Platform Analyzer. So Platform Analyzer is now an offline analysis tool. It's a timeline-based analysis tool. So basically, you take a 5-second trace of your game, bring it into this offline analysis tool, and then you can look at primarily like your CPU, GPU balance and figuring out whether you're GPU or CPU bound. So last but not least, and this is probably the bread and butter of GPA, is Graphics Frame Analyzer. So Graphics Frame Analyzer takes a single frame of your game, so just from present to present, and displays it in a really meaningful way, showing you pretty much all the information you need to know. That's your resources, your shaders, your individual draw call timings, basically drill down as far as you need to go to be able to optimize the minute details of a specific frame or a representative frame of your game. So we'll show that all in the demo, which is great, but that's kind of what's inside Intel GPA. So how do you use this thing, right? It's kind of complex. We have now 3 tools and a monitor, right? So it's actually pretty simple. You just move from left to right here. You have your game. You run it with Intel GPA in the live analysis portion. You figure out whether you're CPU or GPU bound in live analysis. That's kind of the goal, right? You want to get a good flavor of saying, how GPU bound am I? How CPU bound am I? Am I a mixture of both? At that point, then you have a decision to make. Then you can capture a frame if you're GPU bound and put that frame in Frame Analyzer. Or if you're CPU bound, you capture a trace and then put that in Platform Analyzer. And we'll show you both of those tools and the live analysis as well. But that's the basic workflow of GPA, right? You have your live analysis portion and your offline analysis portion. All right, so that's a lot of information really quick and some interesting slides. So what's awesome about this tool is that it is free, right? So at Intel, we don't want to have any inhibitors or blockers for you guys to develop awesome games that are performing well on all hardware. So we don't have any licensing, nothing like that. GPA is completely free, so you can go out, go to software.intel.com/GPA, and you can download it, right? So you can try it out. You can test it on your Unity or Epic or whatever engine that you're developing on. Just build the binaries. There's no code changes needed to enable for this, right? So I don't need to have a Visual Studio plugin or instrument my code with markers. I can just basically take my the output, which is my binary, and then load it into Intel GPA and play it and optimize just straight from there. So it's really easy to use and it's free, right? What's better than that? All right, so at this point, let's actually take a look and jump into the demo. Instead of showing some more slides, I think it's better to show the analysis tools actually working and in real time than just going over a bunch of slides. All right, so let's jump in. So kind of go into that workflow. The first thing that we're going to want to do is go to our graphics monitor, which is down here in the bottom right. If we right-click on it, we have a bunch of options. So let's analyze an application. Today we're going to be taking a look at Sun Temple, which is a Unreal Engine sample running DX12 in full screen mode. So here it is. Here's where we can choose kind of our profiles. Those were those triggers that I talked about earlier, if we want to change those or what metrics are shown. Or even change our hotkeys, right? So you can manually capture, but sometimes we have it bound to like Control-Shift. A lot of times Control and Shift do things in the game. So you can change those there if you'd like. So we've thought about that for you. Also, you can select your API versions here. So if you're using a DirectX 12 game, select DirectX 12. If not, select DirectX 9, 10, or 11. So this is DirectX 12, so let's click Run. And then we'll load up here for a second. Then while it's loading, basically how we work is we have an injection layer that when the game launches, we inject into it. And then you'll see our little HUD up there in the top left with some awesome metrics. So the game's just loading up here. Awesome. There we go. Okay. So here's our game. We can kind of walk around, or it's our sample. So this is Sun Temple. It's a beautiful sample. Up in the upper left-hand corner there, we see GPU busy, GPU duration, and our aggregated CPU load. So by the looks of this, by raise of hands, who thinks it's CPU bound? Just by looking at live metrics. Anyone? No? Who thinks it's GPU bound? All right. It's a few hands on GPU bound. Yeah, that's about right. So I would guess it's about GPU bound too. If we look at our aggregated CPU, it's bouncing between like 5 and 15%. If it's a single-threaded application, this is a 4-core machine, so 25% may mean CPU bound, but it's not even there. And our GPU busy it's almost 100% busy, so that's a pretty good indicator, at least right off the bat, what this could be. So since it's GPU bound, if we remember back at the workflow, what we want to do now is we want to take a frame capture. So let's go find a pretty looking scene. That looks pretty nice. We'll hit Control-Shift and C, and then it'll capture a frame. So what did that just do? So when we capture a frame, it basically takes a kind of like a screenshot, but a screenshot that has all the textures, resources, shaders, states, render targets, basically everything that you need to recreate your game in a single frame, so that we can take it and play it back in offline mode and then gather live performance metrics on that singular frame. So the frame files end up being somewhat large, but we can do some cool stuff in Frame Analyzer because we have that frame file. So just for kicks and giggles, we'll capture a trace 2 just to confirm whether we're CPU or GPU bound. So I'll hit Control-Shift-T. That basically saves off the ring buffer. That was about 5 seconds worth of tracing data. So now that we have that, we can exit live analysis here. Alt F4 that guy. And so let's confirm our hypothesis, right? So a lot of us thought it was GPU bound. So let's go make sure that it is. So we'll open up Platform Analyzer here, and we'll open up this top trace. What that's going to do is it's now formalizing and finalizing the results for that 5 seconds worth of tracing data that we took. Should be able to see whether we're GPU or CPU bound pretty easily from this view. So once it finishes, all right. So there's a ton of data here. It looks kind of crazy. So let's actually just zoom in to a very small portion, and we can take a look. OK. So this is a little bit easier to digest. So what's all going on here? So up here, we have our CPU frames. So you can basically see when each of the presents were submitted from present to present. Here's our GPU queue. So when the packets are sent to the GPU, we can see those packets. There's a little dotted line here. Everything above the dotted line is being currently rendered on the GPU. So commonly, what a good, healthy game will look like is basically what you want to have happen is you want the GPU to constantly be rendering things, but not be so backed up to where there's a lot of latency, right? So it's a good, healthy balance between having your GPU queue have work for your GPU, but not also stalling it, right? So here we can also tell that here this dark green is the time that the CPU is actually doing work during the frame. And it's not very proportional to how much GPU work is being done. So this is definitely a GPU bound sample. Whoever raised their hands, yes, you were right, it is GPU bound. So it's definitely GPU bound, not by a whole lot, but it definitely is. So there's room and improvements that we could make for our hardware to make this game run better. And if we did GPU optimizations, we would actually see some FPS improvement out on the other side. So that's kind of Platform Analyzer in a nutshell. I don't want to spend a whole lot of time on this guy. I'd rather spend some more time in Frame Analyzer. So let's go and take a look at Frame Analyzer. So Frame Analyzer, as I was saying, is definitely our bread and butter of GPA. Here we can open up Graphics Frame Analyzer. And let's see here. Come on. Sometimes when you switch your resolutions, it will get stuck. Let me just reopen it here. There we go. Perfect. OK, so here's one of our representative scenes that we took, right? Here's our capture. So if we just open up this capture here real quick, what this is doing again is playing back basically your entire frame is a replay of your game, but in one frame. So here is Frame Analyzer. So there's a lot going on here. So let's take a quick tour. Up here, so there's kind of like 4 sections within Frame Analyzer. The top area here is our bar chart, right? So here we can, what we're currently showing is, let me change this, is every bar is what we consider to be an erg. So what is an erg? Erg is a weird, funny name that we use to basically say an erg is anything that takes up time on the GPU. So it's not just a draw call, right? It can be like a dispatch or a clear call or something like that that actually takes up time on the GPU, but is not a draw call. Yes, the majority of them are draw calls, and I will say draw call. And if I do say that, or erg, they're interchangeable. So that's what that means. So yeah, basically the bar chart is a visualization of the ergs. We can kind of see our entire frame here. There's about 1,700 ergs, so it's a pretty good size frame. We'll kind of go through this in a little bit more in detail. Over here on the left-hand side, since this is a DX12, we have command lists. So we can see our command lists and our API log. We can kind of go through and look at what's inside each of these command lists. Like here's some draw calls or whatnot. Here in the center area is our resource viewer. So if we make a selection of one of these calls, it will populate our resource viewer, and then we can see the resources associated with each one of those draw calls. So we'll dig into that a little bit more in just a second. And over on the right-hand side, the last panel is our metrics panel. So this is the goodness of Intel GPA. This is how you actually get your raw data, which is cool. So let's talk about some of the cool things in Frame Analyzer. So as I was saying, Frame Analyzer captures this frame, right? Why do we need to capture this frame? It does some really cool things called playback. So this isn't just a data reader, but it's also like a analyzer in itself to where we can do real-time playbacks. For instance, let's take a look at some of these things real quick. One of the things that we can do in playback is, for instance, if I went into my states, so here's a draw call, it's a piece of geometry. Let's figure out what this is. It looks like it's this portion of the ceiling up here. If I wanted to just, let's say, remove it, what would happen? I can click there, disable that erg. It re-renders my entire frame with that piece of geometry missing. So I can sit here and I can just mess with my frame, remove things, replace the textures with 2x2 textures, turn on and off the depth, basically do experiments and then get the results back in real time. So for instance, this saved us 555 microseconds. I mean, obviously we just took it out of the game, so it's all upside from there. If we just, the fastest game is a black screen, right? So it's not what we're trying to do, but it's one of those things to where, like, if an artist put a 200,000 polygon tree in the background and you're like, what would my game look like without that? You could do it with GPA. That's one of the instances that you could use it for, but other things that are common is like turning off the stencil or turning up depth just to see your performance upside, right? It's a good way to be able to bookend your performance. So a couple other cool things that you can do that are DX12 related. Let's kind of go back up to the bar chart here, right? So one of the first things I always do when I'm looking at a frame is I access my bar graph by GPU duration and GPU duration. Basically, that allows me to see the biggest, fattest bars of the things that take up the most time on the GPU, right? So by looking at this, we can say, okay, here's our biggest bar. What is this? So this is a compute shader that is obviously taking up the most time. Great, I can go in, I can look at my shader. If I just scroll down here a little bit, since this is just a built binary of the game, they're using pre-compiled shaders, so all we really see is the assembly. Which is fine. If you want to see like HLSL, basically don't pre-compile your shaders, compile at runtime, and then we can show you your HLSL. You can sit in here, you can edit it. Just how I showed you with the disables erg experiment, you can sit there, edit your shaders, play with it, and then see your performance in real time. Right? So the value here is fast iterations, really fast iterations. So some of the other cool things that you can do are you can region and group by regions. So for instance, all you guys that are using engines, one of the biggest actual rendering optimizations that you can do is batch things accordingly, right, or correctly. So one of the best things that you can do is go by like your pipeline state and then turn the grouping on by that. And then if you see that you have a bunch of like little pipeline states like this, try to group those, because if you're switching states, that's expensive, right? So a good batching will have few pipeline states, or basically few state switching, and you'll get better performance, right? So like for Unity, for instance, doesn't use instancing, it uses just state batching instead of that. So this is a good way to be able to visualize how well your game is actually batched. There's a whole bunch of other stuff in here too. So for instance, let's take a look at the resource viewer for a second and kind of look at some of the resources that are available. Here we split our resource viewer by 3 different sections, right? So if you're wanting to really understand your render and what is exactly happening in each portion of it, you can basically look at the inputs, the execution, and the output, right? So I click on a draw call. These are all the inputs to my draw call. You know, here's my G buffer. Here is another texture. I have some other buffers that I can look at. Here's my geometry. This is a full screen pass, so it's kind of boring. Then I can actually see my states that are associated with this draw call. Then I can see my shaders, which are awesome. I can see how active they are, how often they've stalled. And this one doesn't look like it has any idle time, but you can also see idle on here. And then my actual output. So we highlight the output in kind of this magenta color. If you want to see what it is without the highlighting, that's what this, basically your render target would look like after this draw call, which is pretty cool. So those are some of the interesting things you can do with Intel GPA in kind of a nutshell. There's a ton of extra stuff you can do here. There's this, we've just kind of barely touched the tip of the iceberg with the features on this thing. But I kind of want to open it up for questions at this point. We have about 5 minutes left. So let's open it up just to kind of see what you guys have experienced with optimizing, if you could use this tool, it's free, or any of your experiences. So let's open it up for questions. Any questions? No one optimizing? Yeah, back here.
I just want to ask, is there a Mac SDK for this as well? If you want to test your application on the Mac platform for iOS devices?
Not for iOS, unfortunately, but for like Mac OS for OpenGL, or yeah, we do support that. So okay. Yep, for OpenGL and OpenGL, yes, but not for iOS.
All right,
so.
Thanks.
Yeah, no worries.
I have a question.
Yeah, go ahead.
Is there any sort of like ability to say, oh, my target platform is such and such, or I'm going for Windows 10 at DirectX 12, and it could potentially like come up with like an automated list or a checklist of kind of like, here are things that are maybe red flags, or is it all very manual focused?
Yeah. So we've gone back and forth on that kind of capability. We used to have something that basically made performance suggestions to you. We took that out in favor of doing a more manual approach. So this is kind of the result of that. So currently, yes, it's manual. If you have some good ideas about how we could make that a really useful experience, because that was something that we ran into, was saying, okay, everybody's game is so vastly different to where it's hard to make always 100% correct assumption about somebody's render, right? So yeah, if you have any suggestions on that, please let me know if you had any ideas or whatnot. But yeah, that's kind of the state of that one.
So how well does this transfer over to the mobile platforms?
Yeah, so we support Android completely. So basically, it's the same similar type of workflow. You take System Analyzer, which is the standalone version of the HUD that I showed, and basically you just choose your application and automatically injects it through ADB, and then you basically have the exact same workflow of capturing frames and traces. So it works really well on mobile. I've worked with a lot of mobile developers, actually helping them optimize their games with GPA. So
you can see that kind of a screen?
Oh yeah, yeah, it's exactly this screen, actually. So you can view your render targets or whatever you want to do for mobile. So yeah, it's very useful.
Do you have up on the web any suggested best practices for when we're sort of using this to debug games? Yeah.
So we have quite a few different articles. Jeff Roos is over here. His team is the game enabling team, and they put out a bunch of articles. Like one of my good friends, Cristiano, just put out a Unity optimization guide for people using this tool and best practices for if you have a Unity game, what are some of the things you want to look out for, right? So there's some great resources out there online. I'd be more than happy to hand those out to you and get those to you. But yeah, there's some really good pieces of information out there just about how to use this tool to optimize common problems found, especially within the engines. You know, we also have a really great user forum if you have any questions about optimizing in general or using these tools. So there's a lot of developers out there and a lot of experts on hand that are more than happy to help you. So.
Do you have any memory analysis tools?
Yeah, that's a good question.
In particular, like if you're looking for how fragmented your stack is, or like just trying to help the
yeah,
garbage
so
collector out.
nothing, not for what you're looking for. So basically, our memory analysis pretty much goes down to how much data is being read in and out of our GPU memory. So like we have our GTI right here. So our GTI, that's GPU thread. It's somewhere in here. Basically our GTI read and write. But at that point, you're looking for actually like, here is how much space my total memory is versus how much of whatever texture I'm using, how fragmented it is, or how fragmented it is. So yeah, we've played with the idea of doing something like that. Generally, we don't run into that issue as often on our hardware. You know, that's really common on like iOS, right? That's one of the major things that you find with the iOS platform is memory fragmentation and really optimizing your memory. So we have not focused on that yet. That's definitely something that we might do in the future though. So stay tuned. Cool. Any other questions? Cool. Thanks everyone.